In this screencast, you will learn about the relationship between growth and decay factors and percent changes. We start with a motivating example. In this example, we consider a variable called x. Let's look at part A. Complete the following table. Round all values to 2 decimal places. This example will provide a very good review of the other ways of representing change in a variable. Okay, let's look at the first row of this table. The total change in the variable x in this case would be 15 because the final value of x was 45 and the starting value was 30. That gives us a total change of 15. Now let's calculate the percent change as a decimal. Recall that we calculate the percent change by taking the total change and dividing by the starting value. In this case, that's 15 divided by 30, which gives us 0.5. If we write that as a percentage, it corresponds to 50%. Now let's calculate the factor. This variable is growing. It's going from 30 to 45, so we should expect a factor that's larger than 1. We calculate the factor by taking the final value and dividing by the starting value. In this case, that's 45 divided by 30. If we perform the division, we arrive at 1.5. Finally, let's write the 1.5 as a percentage by moving the decimal point 2 places to the right. That gives us 150%. Now let's look at the next row. In this case, the variable is decreasing in size from 60 to 50. That corresponds to a total change of -10, negative because of the decrease. The percentage change is found by taking the -10 and dividing by the starting value, namely 60. When I perform the division, I arrive at -0.17 when I round to the nearest 2 decimal places. If I write this as a percentage, I get -17%. Again, the negative refers to the fact that the variable decreased in size. Let's calculate the factor. I take the final value and divide by the starting value, 50 divided by 60. When I do this, I arrive at 0.83 when rounded to 2 decimal places. If I write this as a percentage, I get 83%. Now let's go ahead and do the third row. In this case, the variable increased from 40 to 50. That's a change of 10. The decimal representation of the percent change is found by taking that 10 and dividing by the starting value of 40. When I do this, I arrive at 0.25 or 25%. The factor is found by taking the final value and dividing by the starting value. In this case, we arrive at 1.25 or 125%. Now let's look at the final row. Here the variable is decreasing from 50 down to 30. This is a change of -20. The percentage change written as a decimal is found by taking the negative 20 and dividing by the starting value of 50. This gives us negative 0.4, or negative 40%. To calculate the factor, I take 30 and divide by 50, the final value divided by the starting value. That gives us 0.6, or 60%. Let's go ahead and look at part B. There is a relationship between the percentage change and the factor. Can you find it? Here I've given you a hint. What happens when you add 1 to P? The table in part A can give us some intuition for what the answer should be here. So let's look at the table. Let's look at the column that has our p-values, our decimal values for the percent change. Let's add 1 to every one of these values. If I add 1 to 0.5, I get 1.5. Notice R is 1.5. If I add 1 to negative 0.17, I arrive at 0.83. Notice that R is 0.83. If I add 1 to 0.25, I arrive at 1.25, which is R. If I add 1 to negative 0.4, I arrive at 0.6, which is R. So I think the table above suggests that if we add 1 to P, the result should be R. And this is a crucial relationship between the percentage change and the factor. Now let's look at part C. If we think of the factor as a percentage, as we did in the final column of the table in part A, what does it represent? We can get some intuition for this by starting from our equation in part B. Notice that the values in this equation are all decimal representations of percentages. Let's go and rewrite this equation with percentages instead of decimals. So we'll do this one term at a time. 1, written as a percentage, is of course 100%. I add to this the percentage representation of P. That's capital P, percent. And then we have our factor. The R is a decimal. If I want to write it as a percentage, I would move the decimal point 2 places to the right. This is really just accomplished by multiplying R by 100. So I take 100 times R, and that gives me the percentage representation of the factor. This equation that we've just written is equivalent to the equation above. This equation is written in terms of percents. This is the decimal representation version of the equation. Now, what is this equation saying to us? Well, we know that the P% represents either the increase or the decrease in the variable. This is our growth, or alternatively, how much decrease took place as a percentage. In other words, this is how much we gained or we lost in terms of a percentage. We're adding that onto 100%. The 100% reflects our starting percentage. we have 100% of our starting amount. So we're taking 100% of our starting amount and we're adding our percentage growth onto that. So when we're done, we should arrive at our final percentage. That's what this represents. This is our final percentage. It's also thought of as the percentage that's remaining after the change took place. So just to recap, this is what we're starting from. We're starting from our initial value of the variable. We have 100% of that. That's our reference point. We're adding on to that the increase or the decrease that took place. This is what we have afterwards, after the change took place. You can think of this as the percentage remaining after the change took place. Let's go ahead and do a quick summary. If a variable increases or decreases by p%, then what we've seen is that its growth or decay factor R is equal to 1 plus p, where p is the decimal representation of the percentage change. If the factor R is written as a percentage, then it represents the percentage that remains after the variable increased or decreased. Let's go ahead and do example 2.18. For each of the following percentage changes, calculate the corresponding growth or decay factor. Go ahead and pause the recording now. Work the parts of this example on your own. Then continue playing the recording to see this example worked. Okay, let's go ahead and work part A. In this case, there was a 7% increase in the variable. A 7% increase corresponds to a little p value of 0.07. This is the decimal representation of 7%. R, our factor, is therefore 1 plus p, which would equal 1.07. So in this case, R is a growth factor. It corresponds to a 7% increase in the variable. Let's look at part B. In this case, there was a 12% decrease. Therefore, p will be negative. I write p as a decimal, namely 0.12, representing a 12% decrease. R, our factor, is 1 plus p, which would be 1 plus negative 0.12, which gives us 0.88. So in this case, the variable changed by a factor of 0.88. Let's look at part C. Here there was a 100% increase. P is the decimal representation of 100%. In this case, it would be 1. R, being 1 plus P, would then be 2. So, in other words, if a variable increases by 100%, what we're really saying is that the variable is doubling in size. Let's go ahead and look at the next example. For each of the following growth and decay factors, calculate the corresponding percentage change, then specify whether an increase or a decrease has occurred. So in this example, we are given the values of the factors, and we are asked to determine the percentage change. This is just the opposite of what we had to do in the previous example. So we still start from our equation, R equals 1 plus P, but in this particular case, R is known. We know these values. We need to try to determine P. We can do this by rewriting the equation. The equation currently says that R must equal 1 more than P. Well, if R is equal to 1 more than P, then I should be able to calculate P by taking R and subtracting 1. This is an equivalent equation. You can use this equation to determine the percentage change whenever you're given the value of the factor. Let's use this to complete the parts of this example. Here, in part A, R is 1.75. So P will equal R minus 1. So I take 1.75 and I subtract 1. That gives us 0.75. This corresponds to a percentage change of 75%. It's positive, and because this is positive, it means that this is a percentage increase. So this variable, when it grew by a factor of 1.75, really what it did was it grew by 75%. Let's look at part B. R is 0.8. To calculate P, I take my R value and subtract 1. This gives negative 0.2. Therefore, written as a percentage, this is negative 20%. This corresponds to a 20% decrease. The negative represents a decrease. So when a quantity changes by a factor of 0.8, really what is going on is the quantity is decreasing by 20%. Let's look at part C. The factor here is 3. Therefore, little p, which is equal to R minus 1, would be 2. If I write this as a percentage, I get 200%. This is positive, therefore it's referring to an increase. So if a quantity grows by a factor of 3, really what it is doing is growing by 200%. Let's go ahead and look at the next example. Suppose the concentration of a contaminant in a lake is 2.4 parts per million. Determine the resulting concentration if, and then we have two different considerations. Let's look at part A. In part A, the concentration changes by a factor of 1.2. Our goal is to determine the resulting concentration afterward. We know that the starting concentration in the lake was 2.4 parts per million. That's our starting value. We're told that it grew by a factor of 1.02. We are trying to determine the concentration after the change took place. That's V2. We learned in a previous screencast that we calculate the final value by taking our factor and multiplying by the starting value. In this case, when we multiply 1.02 by 2.4, we arrive at 2.448 parts per million. This is the abbreviation for parts per million. Let's look at part B. In this case, the concentration changes by a factor of 0.97. So R here is 0.97. We calculate the ending concentration in the lake, V2, by taking 0.97 and multiplying by the starting concentration, namely 2.4 parts per million. The resulting concentration is 2.328 parts per million. Notice that in part A, because the factor was larger than 1, the concentration in the lake increased from 2.4 to 2.448. In part B, the factor was less than 1, and this corresponded to the concentration of contaminant in the lake decreasing from 2.4 to 2.328. Let's work part C. In this case, the concentration increases by 3%. Here we're not told the factor by which the concentration has changed, but rather the percentage by which it's changed. If it has increased by 3%, this corresponds to a p-value of 0.03. From knowing the p-value, we can go ahead and calculate the r value, because r is 1 plus p. So r in this case is 1.03. So the final concentration of contaminant in the lake is found by taking 1.03 and multiplying that by the initial concentration, which was 2.4 parts per million. The result is 2.472 parts per million. So that's the final concentration of contaminant in a lake if the concentration grew by 3%. Let's look at part D. Here the concentration has decreased by 1%. This corresponds to a p-value of negative 0.01. We can calculate the r value, the factor, by using 1 plus p. If I take 1 and I add to it negative 0.01, I arrive at 0.99. So the final concentration in the lake is 0.99 times 2.4 parts per million, which gives us a final concentration in the lake of 2.376 parts per million. Let's go ahead and look at the next example. Suppose that the current size of a population is 6.8 billion and that the population is expected to grow 4% every 5 years for the next 20 years. Determine the 5-year growth factor for this population and then use the growth factor to complete the following table. So the first thing we need to do is calculate a 5-year growth factor. We're told that every 5 years the population grows 4%. So every 5 years, on every 5-year period, we know that little p must equal 0.04. Consequently, our growth factor on 5-year periods, which is found by taking 1 plus p, would equal 1.04. That is our 5-year growth factor. We can use that to complete the table. Now let's go ahead and actually look at the first row in our table. It shows time, representing years since the current year. It's worth pointing out that the time periods that are shown in the table are 5-year time periods. Therefore, we can use our 5-year growth factor to calculate population values in different years. Let's go ahead and do this. In the first 5-year period, the population grows by a factor of 1.04. 6.8 is my starting value. So I take 6.8 and I multiply by 1.04. That will give me my population 5 years out. When I do this, I arrive at 7.1. To calculate the population in year 10, I use the fact that this is a 5-year period. During that period, the population again grew by a factor of 1.04. Here, the starting value is 7.1. So I take 7.1 and I multiply it by 1.04 to arrive at my population value in year 10. What I arrive at is 7.4, again rounded to the nearest tenth. To calculate the population in year 15, I recognize that this is a 5-year period again. Over that 5 years, the population grew by a factor of 1.04. My starting value is 7.4, so I take 7.4, I multiply that by 1.04, and I arrive at 7.7 when rounded to the nearest tenth. Finally, to calculate the population in year 20, I recognize that this is another 5-year period. Over that period, the population grew by a factor of 1.04. My starting population value is 7.7. So I take the 7.7, I multiply it by 1.04, and I arrive at 8. We conclude this chapter by pointing out that you now have 2 different ways to calculate growth and decay factors, and they are equivalent to each other. We summarize the 2 approaches below. Suppose that the variable v starts from the value v1 and it either increases or decreases by p% to a final value of v2. Then the growth or decay factor can be calculated in one of 2 equivalent ways. First, let's look at the first approach. We can calculate the factor by taking the ending value and dividing by the starting value. We talked about that in an earlier screencast. In the current screencast, we learned that you can also calculate R by taking 1 plus P, where P is the decimal representation of the percentage change. Both of these equations enable you to find R. Which equation you ultimately use depends on the information that's given to you. If you're told what the percentage change is, calculating R this way will be most effective. If instead you're given information about the starting and ending values of the variable, then calculating R this way will be easiest for you.